हां.
ಮೇಲ್ ಐಡಿ ಹೇಳಿ ಬಿಡುತ್ತೆ ನಿಮ್ದು. ಕಳಿಸ್ತೀನಿ ತಡಿಯಪ್ಪ. ಭವ್ಯ DB ಅಲ್ಲ ಮೇಡಮ್? ಕಳಿಸಿದ್ದು ನೋಡಿ ಮೇಡಮ್, ಮೇಲ್ಗೆ ಕಳಿಸಿದೆ. ಅದು ವಾಟ್ಸಪ್ ನಮ್ಗೆ ಸಿಂಕ್ ಆಯ್ತಾ ಇಲ್ಲ ಯಾಕೆ?
ಸಾಕಲ್ಲ ಇವತ್ತು ತಗೊಂಡೆ ಅಷ್ಟೇ.
Good morning, Jatish sir. Hello, Jatish sir. Jatish sir, whether I am audible? Jatish sir. Sir, unmute yourself, sir.
Yeah. Is it okay?
Yeah, very good morning, sir.
Good morning. Good morning.
Yeah, it's okay. It's okay now, sir.
All right.
Bhavya ma'am, over to you, ma'am. Mamta ma'am. Mamta ma'am.
Mamata BS, Associate Professor from Department of Computer Science and Engineering. Welcome you all to today's session. We have entered into the day 2 of the FDP on machine learning using Google Colab. Mr. Jatin Chowdhury has already given introduction to machine learning, overview of Google Colab, the machine learning stack, linear regression and logistic regression on the first day. In today's session, he is going to cover the topics like decision tree, k nearest neighbor algorithm, and random forest algorithm, which are an ensemble learning method for classification. So we shall start today's session. It is over to Jatin Chowdhury. Thank you.
Ma'am. Good morning to all the participants. I hope you had some good learnings yesterday, and I offline received a few of the queries from you on yesterday's topics from Professor Bhavya. So uh, I will try to address those and keep those in mind while trying to take today's session. So let's begin today's session. So day 2. I would just begin sharing my screen. All right. Now I hope my screen is visible.
Yeah, it's visible, sir.
All right. Great then. Yeah, so welcome to the day 2. On today's agenda is these 5 things. First of all, we have doubt clearing session on yesterday's Q&A. Then we kind of towards the end covered logistic regression yesterday and could not see the practical example through Colab notebook. So we'll be doing that. Then we'll follow it up with k nearest neighbor algorithms, decision trees, and random forest. So going back to the doubt clearing session, these were the posted questions from yesterday, like where to get the data sets from, what is the format of data sets, how to create a data set, and how to create train test partition in the data set. So without wasting any time, this is a concise links I put together where you can get real world data sets. Like toy data sets you can create on your own using an Excel or randomly writing XY points. But this UC Irvine machine learning repository is a well known repository where you can get hundreds and thousands of real world data sets with real world use cases. You also get benchmarks so that you can benchmark your solution to the problem with respect to the given benchmark and see where all your solution scores. Then Kaggle or Kaggle, howsoever you pronounce it, is a very famous data competition website where there are data competitions going on. You as a student or as a team, along with your professors or guides or even your friends, can make a team and participate in these competitions. These competitions are more than real world. Like what you will find at UC Irvine is a repository which dates back to 20-25 years, 30 years of data. Even older data is there, but Kaggle is like very real time, very real world, very recent data that you'll get, and those are real world problems. And plus the added motivation is that you get uh, prize, you compete for a prize, you compete for a leaderboard position. So you can go create your Kaggle account today and get the data and practice. Plus other users share their work, share their code, so you can see and learn from the leaders as to what did they do differently than what you were doing. So that is a good way to start. There are Amazon's AWS datasets. Then there are some portals like data portals and QuantL and Open Data Monitor. And then you can get Wikipedia's list of machine learning datasets. You can click, I'll provide these links, and you can go to these links and see some popular open data repositories. Now, data is today's oil, as they say. It's today's currency. So everybody very well safeguards their own data, and therefore it's difficult to find open data repositories. But some companies or some organizations do open their data to external users. So like you can even mine Twitter's data. Like Twitter gives an open API to mine their past 7 days data, not beyond that. So you can retrieve those tweets and do all your analysis and what you want on that. So these are some of the real world data sets you can get. And then other question is, how do you create data sets? So I would say that a data set is nothing but, as you saw, that it's a combination of x's and y's, right? So x is a multi-dimension numpy array. So you read a little bit more on how to create multi-dimensional numpy arrays, and read a little bit on pandas data frames, and that's it. A data set in its most simplest term could be an Excel file or a CSV also. We all know how to create CSVs. It needs to have headers separated by commas, followed by data which is separated by commas. So creating a data set is very simple. Once you create a CSV, you can use pandas to read the CSV, and that's your data set. Now, an important question was, how do you create train or test partitions? Now, we were lucky that in our first exercise, Google had already created train and test CSVs. But when it comes to creating train and test partitions from scratch, how would you go about doing that? So first of all, the data should be ran. The data should be shuffled. You should shuffle your data so that there is no intrinsic order in the data. And so what I show you here is how actually a split train test function would work. That you get the length of the data, and then you create permutations, random permutations from the data, and then you set your test set size to the test ratio. Let's say I want a 80-20 ratio in my train and test split. So I will call this function with my data set with a 0.2 ratio. Now when this 0.2 ratio goes here, let's say there are 100 samples. Okay, let's say there the housing data set contains of 100 samples. When it comes here, the length of data is 100 multiplied by test ratio 0.2, it becomes 20. So your test set size becomes 20. Now your test indices will be this shuffled indices from 0 to 20. That is 0 to actually 19. 0, 1, 2, 3, 4 till 19. All those 20. And then your training indices, I mean not 0, the shuffled indices, like whatever is stored at the 0th index till the 19th index will become your test index, and train indices will become like from 19 on, from 20 onwards, like 20, 21 till 100 will become your train indices. So when you subset this data on these train and test indices, that becomes your train and test split. Now an important thing to note is that this np.random permutation function will always give a random permutation. So each and every time you call this function, it will give you a new permutation. Now why is that a problem? Because yesterday we focused on a very important thing, that your test data should never leak into your train data. So if you call a, if let's say you call a split train test function again and again for, let's say, hundreds of times or thousands of times, you're trying to train your model, tune your model. So ultimately what will happen, your test data will start leaking into your train data, because randomly the test data will get selected into train. You will not get consistent results, and then you will end up leaking all your data or training over all your uh, data, including the test data. Therefore, rather than writing this function like this, we insert a line here which says np.random.seed and give an integer. As long as you keep the integer the same number, uh, the random permutation generated will be the same. So this is a seed to the random function generator. So this is important for reproducibility and making sure that the test data does not leak into the training data. All right. So but what happens is that, let's say you had, first you had 1,000 uh, rows in your data set originally, and you created a 0.2 ratio train test split. So you got 800 and 200 records for your training data and test data. Now, after running this code for a while, after putting your machine learning algorithm into production, now you have 2000 rows at your data set size. You've collected more data, now it has become 2000 rows. Now, what will happen is that once the data gets updated, once more rows get added, now this scheme of ours will fail, because now it will select 1600 random samples from the data and 400 for your test, and may include some earlier test in this new 1600. So what we do, we probably apply a much more complex scheme wherein we generate a hash and try to see whether it has been stored earlier or not. And this is a complex looking function. I don't expect you to understand it in the first pass, but we are trying to see whatever has been included in the test previously should not be included in the train now. So that is what we are trying to do here. So with this new, we pass the index column and keep on checking whether the index had already been included in the test or not. If the index was in test, then we do not include it in the train, in the new train. So this is how you can implement your own train test split. However, you don't need to write these functions and directly use sklearn's scikit-learn's train test split uh, function, and we will see how we do that in our code today. So I hope this clarifies your data set related doubts from yesterday. And so now we will go back to our uh, logistic regression exercise of the classification and uh, multi-class classification and exercise from yesterday. And this was the iris dataset that we were talking about. And as we explained that there are 150 iris flowers from 3 different species, Setosa, versicolor, and virginica. And we need to create a classifier which can identify or associate a class when it is given an instance with sepal length, sepal width, petal length, and petal width. This is what it needs to do. All right. So we'll quickly head over to our Google Colab. So this data set is available in sklearn, and so this package sklearn.datasets contains this load iris function, and you can import that. And similarly, from linear model, you import the logistic regression model. It's connecting. Just give it some time. All right. So I colon xy is equal to load iris, return xy is true. What it means is that if I will directly call this function, then it will return me a data bunch. And this bunch will have data, target, and all the other description features and all these other things related to it. When I say return xy, it splits the independent variable and the target variable and directly returns to me in x and y. So let's see what they are. This is x, this is y. So let's see what y is. So as you can see, y is 0, 1, and 2, where 0 means, so this is a coding for these 3 species. 0 is Setosa, 1 is versicolor, and 2 is virginica. So this is a encoding for this. Now recall our learnings from yesterday. Let me show you a little bit of X also. So let's see the first 5 rows of X. So this is the 4 features, and these are the 5 rows of those 4 features. And if you see, just a second, let me just All right. So if you see the first 5 rows of Y, then all of them belong to the same species. All right. So now the point is that why shuffling is important. So these the target variable or the data set is arranged in the order of the species. If you see, these are all zeros, these are all ones, and these are all twos, which means that if I just go and create a 80-20 split, I will come to somewhere around here. So my test set will contain all two, whereas my train set will all contain all zeros and ones. So therein lies the problem. So I need to shuffle them so that the training set and the test set is a true representative of the actual population. All right. So again, it's very simple. You initialize the logistic regression model. So this is my model, and then you fit it on X and Y. So herein I have called it in one line. If you remember from yesterday, you could have initialized it and then called clf dot classifier dot fit xy. So I've initialized it and called the fit simultaneously. I mean by chaining. Now I predict on X. So this is the prediction it makes. Okay, I have tried to predict it on the same values. Now you can see that the accuracy is pretty high, but if you look at the input, these were arranged or in zeros and then all ones and then all twos. But if you look at the output, the zeros come out to be perfectly fine till here. So I think the zeros have all been, the classification has been spot on. But for the ones here, if you see, there's a classified 2 here, and then one more 2 classified here, one more 2 classified here. So you see that at least 3 of the ones have been classified as 2. And when we come to the twos, again, you see some of the twos classified as 1. So you see that in your test, in even after putting all the data as our training data and testing on the same again, the classifier makes some wrong classification because we assume that our data is right classification. Maybe the data itself has wrong classification, but the data is from nature, and here you are trying to put a mathematical model on top of this nature. So this means that the classification models kind of replicates that the math in that nature to an extent, but not perfectly. And this is what the assumption is. I'm pretty sure if even you saw 3 species of the same flower, there'll be certain doubt in your mind as to which species is this, right? So always remember that most of the machine learning models will never go beyond a human performance in terms of being spot on. All right. Now, so how does this predict? So if you, for the first 2 records, if I say this is the probability that it gives, and internally the predict function takes the class of whose probability is the highest. So the first 2 have been predicted 0, so you can see their probability is the highest here, right? All right. So if we score this, the model has 97.33% accuracy. Is there a question there? All right. So if this is not all right, so if this is not clear, let me try to run this in a better way. So right now I imported the data set from sklearn, and then there is another library called cbond in which the same data set is there, but it is a little arranged in a different manner, and we'll see how. So we import these packages and then we load the data. So now the data, the species this time are categorical variable directly rather than these encoded values which you saw earlier. And then again, so here we will so from this data set we will prepare our x and y. So what is the x? The x is the first 4 columns, and then y is the 5th column. So by doing this data.ilog, all rows and all column except for the last, and data.ilog all rows and the last column. So this is what these mean. So we prepare our train and test set. Remember earlier we had directly called return xy true, so it directly returned us xy. Otherwise, if we would have done false, then we would need to extract the data and again do something like this on top of the data to get our x and y. Now let me show you why this time. Okay, now instead of just zeros and one, this is a categorical variable. Internally the model still needs to convert those categorical values into zeros and one and do a encoding of these, because the model only understands numerical values. But you will see how friendly this becomes. So now we will try to see, first explore the data and see how does the 4 values in correlate with each of the species. So this is the spread. Okay, so if you can just draw a vertical line from here, all right, and if your petal width is somewhere between 0 and 1, then you yourself can say that to be safe it is of Setosa species, right? So you can even say, by some visual analysis you can even say that even if petal width is around more than 1 but less than 1.5, then you can even say that directly that the species is versicolor. So some partitions you can do by even manually observing this, and even your machine learning model internally does something similar like that when you switch to something like a decision tree, and we will see that later in our session today. So, and this was the function that I was talking about, train test split. Okay, so this function I have included and imported from this package called sklearn.model selection. So you don't have to write that complex function on your own. It will split your x and y into your training sets and the test sets. So we split it into 80-20 ratio, initialize it with a random state so that the outputs are reproducible. The rest of the is a pretty drill that we've learned, that you create the model, instantiate the model object, then call the fit method on it. So it has trained fast. Now we predict our test set. Earlier we were using the whole data to predict our entire data. Again here we are doing it in a better way, the way machine learning is supposed to happen, that you have a train set and a test set and then you predict on the test set. All right. So now instead of zeros and ones, you see that for these 20 samples, it has directly given the categorical value what it is predicting. All right. Now, one thing to note, let me just put a few prints here. All right. So this is our prediction. Now, accuracy score on test is 1, which means 100% it has identified all correct. And these are some scores, or these are some classes. This is called a classification report, where you have a particular measures like precision, recall, F1 score, and support. And we are lucky that in our train test split, because of the random seed that we've given, that we could identify all correctly. But it maybe if you run it with some other random seed, it may not be the case, and therefore it is important for the reproduction of results, that reproducibility of the results, sorry, that you set a random seed always. So we will understand these in probably on our fourth session, that what does these parameters mean. But it's important for you to note that you can generate these classification report and everything just by calling function on the test parameter and then on the prediction. whatever your predictions have come, this prediction. So it will compare the actuals versus predicted and get these scores for you. All right. Okay. So you saw how classifying or generating an answer in this form is better for readability perspective than generating an answer in this form. Ideally, you could easily convert this 0 ones into categorical values by yourself by just including a small step here, but uh, you can even directly achieve that if your data is in the format given here. All right. And we are using this data set we will be using this data set throughout our example so that you can correlate to what you learned earlier and how this differs from something that you did earlier. All right. So one more popular classification in machine learning is the MNIST classification, wherein there are images of these handwritten digits and a system is supposed to predict on seeing an image as to what this digit is. All right. So can you think in your mind as to how would you go about doing this? Just think for a while that you have been given some images and now your model needs to figure out what this image is. Now a model can be only as intelligent as you are, and look at this 2 comma 1 second row first second row second column 2 comma 2. Isn't it difficult for you to figure out what this is? Is this a 5 or is this a 6? So there will be cases, there will be chances where the model is bound to decide in a particular favor more than the other, and those are the things that you try to minimize and figure out. All right, so let's get ahead with this. And so how exactly is an image stored? An image is nothing but a series of encoding in terms of the pixel encodings, that what is the, in case of black and white, whether the pixel is black there or it is white there. If it's a grayscale, if it's color, then there will be 3 components for each pixel, which will be in terms of what is the RGB value. Is the R there? Is the G there? Is the B there? Or it's in different combinations there. So here it is black and white. Assume this to be black and white, and so you have a 2-dimensional array in which you encode each pixel is whether it's black or white. So that is how an image will be actually stored in the memory. So we will go on to our Google Colab and see how this is done. All right. So again, this is from dataset, the sklearn datasets, and how you can obtain this dataset is using the fetch openml function. And then again, we will have a logistic regression for this, and we'll do some scaling for you, which you will use standard scaler. So let's fetch these this data set, and again the return xy parameter is true, meaning it will directly return us x and y. It will return us the image content, what this image is in stored in memory, and then y will be denoting what that digit is. It will be a string, but it will denote what that string is. So it will give us the content of the image and then what the image is. So this, since this is image data, so it's a little heavy, so it takes a little bit of time to come into the memory, and this will take more time if you do it on your own system locally versus when you do it on the Google's cloud. All right, so we have the data. Now if you don't do it without return xy, if because that default value is false, and if you hover over this function, you will get what I'm talking about. There are so many parameters you can manipulate to get the data particular way. So let me do that also for you. So x and y directly have all these. So just a second. All right. So if you load data without return xy, then it returns a dictionary with some keys. There's a key called data, there's a key called target, there's a frame, then feature name, target name, description, details, categories, URL. So these will be all your keys. Now if you just say mnist dot get, let's say description. So this will tell you that the author of this data set is Jan LeCun, the famous data scientist, and then the date is unknown, handwritten digit with 784 feature. It will describe that it has 10,000 samples. All right, but we will not use this. We will directly load our data in XY. So if you see X shape is 70,000 and 784, which means that there are 70,000 samples, and then out of which the shape, the 784 is the number of columns. And why is it 784? Because each image here is a 28 by 28 pixel, and each feature simply represent 1 pixel's intensity from 0 to 255. So it's in grayscale. So what each pixel's intensity is, whether it's 0 white to black, so or it's somewhere in between. So you have 784 such columns and 70,000 such rows. So let's see how each digit looks like. So x of 0 means the 0th record, means the 0th image in our data set. So so this is how the image looks like. And if you try to select y of 0, let's say we figure out what's in our target variable, y of 0. So this is 5. So you can figure out this is 5, right? Similarly, if you see x of, let's say, 10, and let's check on y of 10. So the 10th image, this looks like a 3 to me. Let's see what y says. Yeah, y also says. So y of 10 is also 3. So the target, so you've loaded your x's and the y's. Now it becomes straightforward classification task. You don't have to think much about it. Your input data has 784 rows. You need to split it into test and train, then train on your training set. So you see that the y categorical variable here is, the target variable here is stored as string. So we'll convert this string into integer, and now you see it comes as an integer. Now we initialize a random state and then do the permutation. So initially I showed you that test train split function, right? So here we are manually doing that just because I wanted to show you that this can really happen. So the length of the permutation is 70,000. Now what it'll do is, if I just print the permutation, so these are all the indices, so random indices. So I shuffle the data, x is equal to x of permutation, y is equal to y of permutation, and then I reshape and then use the train test split function where I keep the test size to be 10,000. So 70,000 samples, 10,000 I want as test, and remaining 60 I want as train. Now it's a good way to probably normalize your data. So you use the standard scaler to scale your input data. So you scale both your training and test sets. and then you use some parameters for faster training, and then you fit. All right. So for the first 10 images in the set, this is what the image looks like, and this is what the classification has been predicted. So even with these feeble images, it will be able to predict that what is the image looks like. So to generate these plots in this colored way, you need to do some manipulations, some which are a little complex to be covered step by step. But you can see that you initialize a plot which is a 10 by 5 plot. So figure size is 10 by 5. Then you create these subplots. In each subplot, you put those images and try to color them because now you have scaled your input and your test set, so you can convert that grayscale into a colored image. Yeah. So this is the easiest way in which, and then what you see here is like the penalty is L1, solver is Saga. So these are different solvers. So you know how logistic regression actually works, but to be able to come to that, deciding those coefficients and how do I decide the y-intercept and how do I decide those coefficients. So now imagine when we were doing with 1x, we had the equation in the form of y is equal to b naught plus b1x, right? Now you have 784 such x, so x1, x2, x3 till x784. So now the coefficient will be b naught, b1x1 plus b2x2 plus b3x3, and there will be like b784, x784. So it has to determine all these weights. And how does it determine all these weights? Is using some algorithm, some optimization method. So there are different optimization methods, and you can select one of those methods depending upon your data or depending upon which gives you better accuracy by manipulating the options that are there within your model object instantiation function. So by default the solver is LBFGS, and you can have multiple solvers. The solver algorithm are given here, and you can see which solver is good for what. They also give an idea about, like, for a smaller data set, linear is good choice, whereas SAG and SAGA are faster for larger ones. So this was a larger data set for like 60,000 samples which we have to fit. So we use this, and you can try this on your own and figure out what gives you a better accuracy. All right. Okay. So this is our classification exercise which we had to cover yesterday. Now coming back to the topics that we are supposed to today, and somebody in the chat also asked whether we are going to learn k nearest neighbors. So yes, here it is, k nearest neighbor for you. So pay attention to this algorithm. It is a very interesting, very simple algorithm, and people often mistake this algorithm. And I myself, when I interview candidates, they kind of confuse between k-means and k-nearest neighbor algorithm, and more often than not, they confuse how this algorithm actually works and for what all purposes can it be used. So what is a k-nearest neighbor algorithm? K-nearest neighbor algorithm is a non-parametric method. So what do you mean by non-parametric is the first thing to focus. Non-parametric means that the algorithm does not assume or is agnostic of any underlying distribution of the data points. Like some algorithm works only when the underlying data is normally distributed. All right, but this is a non-parametric method. And the best part is it is used for both classification and regression. So you can use it. KNN classification is also there, and KNN regression is also there. Most of the times we just read about KNN classification and do not read about KNN regression. And this is a very good interview question, that explain KNN regression. And people are suddenly thrown off that, they mostly read KNN classification, but how can KNN be used for regression? So in KNN classification, the output is a class membership. So you have an unknown data point, so the output will be a class. So if you had a flower species, a flower, and you had sepal width, sepal length, petal width, petal length, and you need to figure out which class this is, you can apply a k nearest neighbor algorithm. So what it will try to do is it will try to find k near flowers in the training set and see which class is more near to this unknown data point, and it will assign that class. So the output will be a class. In KNN regression, the output is a property value, meaning in the same data set, if you only have two features like sepal width and sepal length, and petal length is what you are trying to figure out. So for an unknown petal length, for a given sepal length and sepal width, it will give the petal length. So it will be a property value of the object. This value is the average of the values of the k nearest neighbor. Whereas in classification, the class is a majority voting, which is the most common class in the nearest k neighbor. So I will, this is easier explained through this animation. Now look closely at this animation. So these are red and green classes. Now you get an unknown data point here. So how it will decide the class on the basis of three neighbors. So here k is 3. So it figures out three neighbors and see which class is more common. So you can see that we have two reds and one green. So it will assign the red class to this data. So this is the basic principle of KNN. Isn't this simple to understand? But then you say, if this is so simple, why have we trying to, understand, calculate the coefficient, find out the plane, find out the equation? If it's so simple, we could do this. Yes, it is a very simple and straightforward algorithm, and more often than not, it works really fine. In complex cases, things are not so easy. Let's say this. And one question is, how do you decide k? So this white data point is what we are trying to figure out which class this is, and then this k value we are trying to move from 1 to 3 to 4, and this prediction what you see here. So if k is 1, prediction is green. If k is 2, prediction is green. If k is 3, prediction is green. If k is 4, prediction is tie. And if k is 5, prediction is red. So if you see that depending upon the value of k, the prediction went from green to red or green to again red to again green. So what I'm trying to say is that it does not give one final answer. You have to figure out the value of k which is most accurate for your solution. And there are a lot of manual adjustment that you will have to see and look for in the output. So it is not as straightforward. It does not always give consistent response in the first pass. Like how will you decide the value of k is the first question. So you'll have to go through some iterations, figure out what is the most optimal value of k. Now you see there was a tie, right? So one thing to consider is that if there are even number of classes, try to keep k at an odd number so that there is no tie. If the and let's say k is infinitely large, let's say k is equal to the length of the entire data set, then the output will be whichever class is more present in the data set, the output will always be that. So it is very easy for this algorithm to become biased. So the classes need to be really balanced. If you have like 100 classes, if you have like a ratio of like 1:4, then chances are if you cross a certain boundary, it will always say it is class B, which is more precise, right? Okay, so we will see a quick Colab demo for this. So again, we go to our favorite iris dataset. We load the XYs. And then we do a train test split in the ratio 70-30. Let's see what is our Y test. So you see that this is shuffled, right? So this train test split function kind of takes care of shuffling the input. Now we do some scaling. Now what is scaling, if you ask? So basically this standard scaler will standardize the features by removing the mean and scaling to the unit variance. So x minus mu by standard deviation, x minus mu by sigma. So it converts each of these features to their standard values. And when you standardize your x, x train, you also standardize your x test, because the input also needs to be the test input also needs to be of the same range. So now you see that it has standardized, and you'll see some negative values also here. Now why are these negative? Because it has been standardized, and otherwise the length and width cannot be negative of a flower, right? All right. So you instantiate a k neighbors classifier with 8 neighbors. You can keep this, you can vary this number of neighbors and all, and then you fit on your train and x train and byte, and then you predict a test. Let's see what the prediction says. So this is our prediction. Now again we will use our reports to figure out. All right. So you see this confusion matrix, right? This confusion matrix is essential to note. What it means is the class 0 actual is here, the 1 actual is here, 2 actual is here. This is the predicted 0, this is the predicted 1, this is the predicted 2 column. So you see that for there were in your test set, there were 15 ones, meaning the class 1 was 15. But the predicted is, out of those 15, 10 were predicted as ones, but 5 were predicted as twos. So this is how you read this. And out of the 18 class 2s, 8 were predicted as ones and 10 were predicted as twos. So now you see we don't have a 100% accuracy like we were getting earlier on, even on our test set. Now you see that these values are other than 1. There is some precision, some recall on the classes. So on class 0 there is 100% precision. You see all class zeros were predicted as class zeros, all 12 of them. But then here it drops to around, out of 15, 10 were correctly identified, 5 were not identified. So there is drop in precision and recall on this. And then out of 18, only 10 were identified, 8 were not identified. So again, there is some variance in precision. So the accuracy that you can see is 71%. Because some were misclassified. This 5 and 8 are the total misclassification. So 5 plus 8 is around 13, and total number of samples were 18 plus 15, 33 plus 12, 45. So out of 45, around 13 were misclassified. So your accuracy comes to around 71%. So this is how you read report, and not always you go by accuracy, you always also go by precision and recall. All right. Now, as I said that you can use a KNN regression also So what does a KNN regressor actually means? So again, you load your data set, and we will only take the first two columns as input, and we'll try to predict on the third column of the input. So these are our first two columns. Let's say first 10 samples of the two columns, and this is what we will try to predict. The third column, 1.41. So instead of a classifier this time, you instantiate a regressor, and with some neighbors you try to fit and you try to predict. So these are our first 10 predictions. So if you see 1.4 is predicted as 1.46, again 1.4 is predicted as 1.45, 1.3 is predicted as 1.51, so on and so forth. So what it is trying to do is trying to find out the nearest neighbors to this data point, take the average of them and give it to you. And how many neighbors? 10 near neighbors to this data point. So if you see the score, then 94.5% accuracy on the prediction of this. And if you want to see the mean squared error on what it did, then what you will do is actual minus predicted whole squared. So 1.46 or 1.4 minus 1.46 whole squared plus 1.4 minus 1.45 whole square plus 1.3 minus 1.51 whole squared plus so on and so forth, and you will take a average of it divided by n. So you can do this in this one line. You do a y minus prediction whole squared and then calculate a mean on it. So let's see what is the total mean squared error. So our mean squared error on the entire computation of all our samples is 0.71. So if you vary these number of neighbors, maybe you get a lesser mean squared error, maybe you get a greater mean squared error, and then you can finalize on k. Now you would ask that, we already have these y's, then why did we use this k nearest neighbor here, right? This regressor here, right? What's the point? So the point is that in your data, not always all values will be present. So imagine the case where in this iris data set of 150 samples, if 20 or 30 or 50 odd samples did not have petal length, then the only choice with you is that ignore those 30 samples. So your 150 data set point reduces to a 120 data point set. All right. And then you run your algorithm on top of it. Or what you do is for those 20 which are missing, you use a KNN regressor, try to figure out the values of the petal length on the basis of their neighbors, and then run on those 150 points. So what this will do is you'll have at least data on 150 points is more than data on the 120 points. So usually this KNN regressor is one of the techniques used to impute data or to calculate the missing data or to handle the missing values in the data set. So this is one of the easiest way. Another way to impute data is take the mean of the entire feature set. So if those 20 petal lengths were missing, what you could do is you calculate the mean of the 120 petal lengths and then just substitute the missing petal length values with that mean. But don't you think this calculated mean from the neighbors will be better than some absolute mean? Because if you go back to this here, this image here, then you see that the ranges are different, right? And if I say that I will substitute all missing petal lengths with the absolute mean of petal lengths, then I will be filling some values which are not close. They will be a little far apart. So intuitively, it also makes sense to just fill those missing values by their based on their neighbors and not on absolute mean or median. All right. So I hope now there is no confusion regarding what is k nearest neighbor. So k nearest neighbor is an algorithm which is non-parametric. It is used for both classification and regression. It is very simple. It does not depend upon the underlying distribution of data, but at the same time it is very compute intensive. Like for any given data set, it will first calculate distance. Any given data point will calculate the distance of the data point from all other data points. So if this was not 150 and it was 150,000, then to predict one data point, it will scan all the other 150,000 data points, calculate the distance, rearrange the distance, and then take top k nearest distance and then come to answer. So these kind of learn models are also called instance based learning. Remember, we talked about the three categorization of machine learning model. So this is an instance based learning model. Also, it falls into the category of models called lazy learning. So after the instance come, it starts learning. So the learning is delayed and it's called a lazy learning. So those two are often the questions asked, and often you'll see those things in the literature as well. It's a non-parametric, lazy learning, instance-based model. If you were to explain this to somebody who knows data science, if you say these three things, then the person will know that you know what you're talking about and you understand fully what k nearest neighbor means. All right. So I'll quickly take a break of a minute. I'll drink some water. You can also do that. And then we will focus on our next algorithm called decision tree. All right. So we go back to our agenda. Next thing in our agenda today, that is the decision tree algorithm. Before I go to the textual definition of what decision tree is, I would like you to go back in your memory and think of how you took admission in the college. Like you gave an exam, then your rank was published, and then you saw the rank, figured out your aspirations, what you wanted to do, and then you saw all these options of all these colleges, and then you figured out at your given rank of the branch of your choice and probably the city you wanted to study in, what is the best college that you want to go, or what is the best college that you could get. And then you maybe considered some other factors like fees, the faculty, the placement. So you consider a lot of factors while joining the college, right? And if you were to generalize, optimize this thought process, let's say you want to help a junior from your school out in deciding which college to uh, join, you will apply some process to it, right? You will consider all these variables, that what his rank is, what his aspirations are, what her uh, branch of liking is. Then you will do that, and if you formalize this well enough, you will come at a decision process. It will be like a tree, not the usual tree, but the tree that we see in computer science with the root on top, and then you have branches coming out, and then you have leaf nodes in the end. So decision tree is nothing but exactly that. But instead of a question like which college to join, these are other questions like which class this data point belongs to, what is the value of this data point. So you're trying to predict something there. So in a nutshell, a decision tree is nothing but exactly the same. So decision trees are versatile machine learning algorithms that can perform both classification and regression tasks and even multi-output tasks, meaning it does not have to be a 0, 1 or a pass fail or a present or an absent kind of scenario. You can have multiple outputs. They are powerful algorithms capable of fitting complex data sets. Now, decision trees are also fundamental components of random forest, which are amongst the most powerful machine learning algorithms available today. So, decision trees or DTs are again non-parametric supervised learning methods used for classification regulation. So again, the focus is on the word non-parametric and supervised, meaning it does not depend on the underlying distribution. Supervised learning means you will have to tell in your training set what is the class, and it will do both classification and regression. Now, the goal is to create a model that predicts the value of a target variable by learning simple decision rules inferred from data features. The deeper the tree, the more complex decision rules and the fitter the model is. All right, the depth of the tree. So you would have solved some questions in your data structure and algorithm, right? Find the depth of the tree. So it is again talking about the same depth, the height from the root to the leaf. So the deeper the tree, more complex decision rules. Now I would like you to, once again figure that, when you up until now you have been seeing equations, but now you will see a tree with various branching, and there will be rules. So what this decision tree does is makes your machine learning output more interpretable, and you will see in a shorter time as to why. So this is the classical decision tree for playing outside. So the question is whether you can play outside or not. So the three factors to consider is humidity, outlook, and how windy is it. So if you want to play probably badminton, so maybe in wind you should not play, right? But it is okay to play a little bit of football if it's a little windy. All right. So depends upon what kind of sport it is and how the data is stored. You can have a decision tree for playing outside. So if it's so the rule here is simple. So first you consider humidity. If it's highly humid, how is it looking outside? Is it sunny? Is it if it is humid and sunny, it's not probably a good idea to play outside. Is it looking overcast? Then probably you can play. Is it raining and humid? Then yes, you can play. But if humidity is normal and there is too much wind, then you probably don't play. But if there's normal humidity and there's no wind, then probably you can play. So in this way, a decision tree is very simple to read. There is no complex mathematical equation here. But internally, it is coming up with these rules after deriving those complex mathematical equations behind the scenes. Now, you would have seen that these are some advantages of decision trees, that these are simple to understand and easy to interpret. These tree can be visualized. It requires little data preparation. The cost of using the tree is logarithmic in the number of data points used to train the tree. Unlike in classification, where you have to go over the entire data set again and again if you were to classify one unknown point. And it is able to handle both numerical and categorical data. Other techniques are usually specialized in analyzing data set that only have one type of variable. This is very true. So typically a decision tree is my first go-to choice for setting up a baseline. And it is able to handle multiple output problems. Now, if there are advantages, there are bound to be disadvantages. So the disadvantages of DTs are that they can create overly complex trees that do not generalize well. What do you mean by generalize well? That they will perform poorly on your test data. They will perform perfectly on the trained data, but they'll fail miserably on test data. And this problem is called overfitting, and this can be overcome by doing some things like pruning and setting the maximum depth of the tree, etc. And decision trees can be unstable because small variation in the data might result in a completely different tree being generated. And then decision tree learners create bias tree if some classes dominate. So again, the same bias that our k nearest neighbor suffers from, is the same bias that a decision tree would suffer from. But most of the disadvantages can be overcome by using random forest. Most of them. And we will see how that happens once we come to random forest. But let us first go to decision trees. So again, we load our favorite data set. Data set is loaded, and from sklearn we import tree. This is the name of the package from which we can create our decision tree classifiers and regressors. We load our x and y values directly, and then we instantiate a decision tree classifier. First we will do classification, then we will do model.fit on the default values, though you can do a max depth, max feature, class weight, you can do all that, and then we'll plot this tree. Okay, so this tree says, all right, so can you read this? It's a little difficult to interpret, right, reading here. So it also generates a image, but this image is not clear. So what you can do is you can use the GraphViz library to generate a better image. So it generates an image in a PDF. You can download this PDF and see what image it has generated. So let me show you. So this PDF will be generated here in your folder. So this is the iris.pdf. Now if you click on it, okay, it will download this on your desktop. So this is the tree. Okay, so what it means is that x of 2 means the feature the second feature. The second feature, it's a 0 index, so 0 1 2, it's actually the third feature. So but we will go by 0 indexing those. So if the second feature value is less than 2.45, then you come here. So if it's less than 2.45, then you see all the values are 50 0 0, meaning all of those belong to the 0th class, that is Setosa. So you get a simple decision rule that if, let me go back to the feature class here. So it says that if the petal length is less than 2.45, then all of them are Setosa, which is very much clear from this also. If the petal length is less than 2.45, then all of them can be safely considered to be Setosa. This is what it says. And then it says if x of 3 is less than 1.75. So if it's greater than 2.45, if x of 2 is greater than 2.45 and x of 3 is less than 1.75, then it again splits into these two. And then finally, by applying these if else condition, it finally puts each of those samples in some or the other bucket. So this is how you interpret a decision tree. Now again, let me generate this graph in a better manner for you. So by doing some manipulation, you can now read this. Rather than x of 2, it directly reads if petal length in centimeter is less than 2.45, then class is Setosa. If the petal width is greater than 2.45 and less than 1.75, then there are 100 samples. Okay, and then again you diverge, branch out, and it identifies all those classes. So this yellow, orange one is Setosa, this green one is versicolor, and this purple one is virginica. And there is some noise that I am hearing from the background. Please, if you can mute yourself, be great. Yeah. So using this GraphViz export GraphViz function, I can generate this model which you can easily figure out. So Even now, if I give you a random point with the 4 values, that this is the petal length, petal width, sepal width, and I give some random values to you, you will be able to figure out which species is this based on this decision tree. You can read and walk this tree and figure it. Easy, right? Sir, can you please mute yourself? All right. Now, for a decision tree regression, let's create our own data set. And this will answer again the question that how do we go about creating the data set. So we generate some X and Y values. Now let's see what our X and Y values are. So this is what I've generated. I've generated a sine function and then thrown some data points near about those sine functions. Okay. Now I create 2 decision tree regressors with some depth 2 and depth 5. Now remember what we studied earlier, the deeper the tree, the more complex it is, but the more chances of overfitting there are. And I will help you understand how does a decision tree regressor would actually work. So again, we fit both of these regressor objects and then predict. So y1 and y underscore 1, y underscore 2 are our output from decision tree with depth 2 and depth 5. This is our y. This is our predicted y1. Y1 is for depth 2. So you see, for most of the y values, it predicts the same thing, right? So it is not able to capture the essence truly. But for when I go to y2, it is varying. The step is very minimal.
Good afternoon, sir.
And when I plot these figures, you will get the original data set, and then how if the 2 decision tree regressors were to trace these steps, then how will they figure out? So you see that in the max step 2, which is a blue, you have more abrupt steps, lesser variations. So how it will work is, let's say for this data point, it will say if it lies between this value 0 point something and 3 point something, then associate this blue value with it. So this will be our decision tree regression on it. So you see the difference in between the predicted value and the actual value is more. So you see these big steps are there. When the steps are big and they are wide, you are prone to miss out on a lot of features. So you will miss out this curve entirely. But in the green one, if you see, then it is even capturing these outside. You see that even for a small variation, it is bringing the step down and then making the step goes again. So in the green one, you see the steps are narrower. They are maybe a little taller, maybe a little more abrupt, but they are definitely less wide. They are narrow. So when you have narrower steps, the curve is more smooth. So this is how the depth of a decision tree can produce very good results if increased, but then they could also be overfit. So in our case, when we generated this data, maybe this was an actual sine curve. So imagine this reading to be coming from the observation of a sinusoidal wave, but these data points are nothing but the noise caused by, maybe there is some so how do you observe these variation? Maybe the sensor has some noise. So maybe these data points are some noise. So what a tree with depth 5 would do is overfit, taking this noise into consideration. So this noise will also appear in your output. But what with depth 2 would do is it will flatten this sinusoidal. So maybe you need something between 2 and 5. Maybe if you run this with 3, you may get a better output. So what we will do is we'll run this with 3. And see if we can smoothen, if we can compensate this. All right, so let's run this once again with 3. Yeah. Now you see that your red model is kind of capturing this sine wave. You see, if you were to just join these, then you are kind of capturing this sine wave, yet you are not going till the noise. So this thing can be used in filters also. So if you are trying to produce, let's say, some noise cancellation, then this value of 3 can be an excellent way to cancel out that noise in your observation. All right, so I hope that this decision tree, by decision tree you are able to figure out how things work for a decision tree, and then you are also able to appreciate how varying the depth you can make your result better or maybe worse. All right, and it is for this very reason that you get a score function to figure out how you are scoring on your test and train. What you ultimately want is that your model should generalize well. It does not mean that you juice your model to having higher accuracy on your training set. If you overfit your model on training set, then it will generalize poorly on the test set. So you need to strike a balance between your training accuracy and your test set accuracy. All right. So when we were reading the disadvantages of decision trees, like you saw that it could really overfit fast. So most of these disadvantages can be overcome by using random forest. Now what are random forest? So random forest are also known as ensemble learning algorithm or committee algorithm. So what do you do when you have to take a decision? Like it's a complex decision and you want to take a decision. So basically you ask multiple people that what should I do? At least most of the people do this, that they will ask multiple people what should you do, and then based upon their advice they take that decision, right? Now it is important, let's say you are taking a career decision. Again, since most of you are students, so I will fall back to the student analogy, that you have done your class 10 and now for your pre-university or class 11, whichever board you studied in, you want to take a decision whether you want to take maths, you want to take bio, or you want to take commerce. Now a good idea will be to talk to your seniors who've taken, if you want to take, let's say you want to take maths, then you talk to your seniors who've taken maths. But all seniors who've taken maths will probably be biased towards maths. So what a good idea would be to also ask some bio students, also ask some commerce students, that what do they think, so that you have a variety in the input that you are taking. You get a variety in the pros and cons of each and every side, that you are taking, so that you can take an informed decision. Similar to this, any committee which is formed in college, let's say for anything, you form a committee, then you need to have a various talent in that committee, right? You need to have a varied committee in order to be able to come to a good balanced decision. So random forest or ensemble learning methods are nothing but the same, that you aggregate the predictions of a group of predictor. So till now we have seen that you can do the iris classification either using KNN, you can do by logistic uh, regression, and you can also use decision trees for classifying the species of the flowers in the iris dataset. So what you do is you take the predictions of a group of predictor and then you ask them to vote. Whosoever gets the maximum vote, you decide on that. So ensemble math, you can train a group of decision tree classifiers, each on a different random subset of training set. To make the prediction, you obtain prediction of all the individual trees and then predict a class that gets you most vote. Such an ensemble of decision trees is called a random forest. So like the name signifies, right? A forest is nothing but where you have more trees. So if all your predictors are decision trees, then an ensemble of decision trees will be called a random forest. However, ensemble could be of decision tree, k nearest neighbor, and logistic regression. You can create an ensemble, you can create a committee out of different predictors as well. So this is how it works. You have multiple models and these models will vote. Let's say model 1 votes 1, model 2 votes 1, and model 4 votes 1, but model 3 says that no, I think the class is 2. But you take a majority vote and decide that the class is 1. So this is how you do a ensemble prediction. More often than not, an ensemble prediction works much better than any individual predictor. And in machine learning competition, ensembling is a technique that most of the teams use to get the output. So what I will do, instead of showing you a Google Colab, I will give this to you as a take-home exercise that you implement this voting. All right, you implement this ensembling on your own. Now you have different classifiers, each from logistic regression to KNN to decision trees. So what I want you to do is that you just instantiate those three models, and then there is something called a voting classifier in sklearn ensemble. So you create a voting classifier out of these three. So you can, this is a support vector machine, but you could easily replace it by k nearest neighbor. So you replace them, you do a hard voting and train on it, and then you figure out the accuracy from the individual and the voting classifier. So in my case, what I've done is that on the iris data set, the logistic regression was giving me 86% accuracy, the random forest was giving me 89, the support vector machine was giving me 88, but when I put the voting classifier, I got 90% accuracy. So now, as a take-home exercise, you replace this, you either try with support vector machines, which is another supervised learning algorithm, or you replace it by a KNN classifier, and then you create this voting classifier and see the results for yourself. I think this should be really easy and it'll be good exercise to understand how does ensemble learning works. In the same voting classifier, if you replace these by three different trees with three different depth or three different parameters, it will become a random forest. Or you can straight away instantiate this random forest classifier, pass on the parameter, it will automatically generate those trees, create that voting and give you the final output. So this is your take home activity for today. In the next class, I will show you the code for random classifier and voting classifier if there are questions about it. So we've come to an end of today's session. The next 2 to 5 minutes, I will take a few questions if there are. Sir, you can probably open the chat for the questions.
Thank you, Raj. Thank you. Thank you. Continue. ಅವ್ರು ನೋಡ್ತಾನೆ. Thank you, Jatin sir. Myself, Shweta MK. I'm working as assistant professor in the Department of Computer Science and Engineering. Now the session is questionnaire session. Some of the participants were asking the questions about that random state in the linear regression module. The question is, you have taken the seed value in the random state question as the 42 value. Can we use any other values for that?
Yes. But every time you have to use the same value if you want to reproduce the results or if you want a consistent benchmark. So for a given model, use the same value. You can use any value. Not a problem.
If you use any other values, what should be its output?
So a random number generator, if you would have studied, so produces random numbers within a given range based upon some intrinsic random property of the system. So if you put a seed, then it will associate that seed with that random value, and then each and every time, though the inherent properties of those numbers is that they are random, but those same numbers will get generated again and again. So you can put any value, depends
Okay.
upon, yeah. So you can go hover on the uh, random function generator function, and then you will get all the documentation of what kind of values you can have, and you can give any value. You can just do a 0 also.
Okay, sir.
Yeah.
Next question ಏನಿದೆ ರಮೇನ್ ಏನು ಇಲ್ಲ ಅಲ್ವಾ ಅದೊಂದೇ ಇರೋದು.
If there is any other question, Shweta?
Yeah, no more questions, Bhavya. There is no questions in the chat box.
Thank you, Shweta.
Thank you, sir.
You're welcome.
We come to the end of the session of the second day. Once again, I thank our resource person for the valuable time spent on delivering a talk on machine learning using Google Lab. Once again, thank you, sir.
Thank you, ma'am.
ಯಾವ್ದಾದ್ರೂ ಯೂಸ್ ಮಾಡ್ಕೋಬಹುದು.
All right. Shall I end this meeting?
Sure, sir.
Yeah. Thank you.
Thank you, sir.
We'll see you tomorrow. Yeah.
Okay, sir. Thank you. No, we'll charge in.